Hi, this is some feedback on PAG 10.4. This was your initial rates experiment. We called it the disappearing cross experiment. So this is where you did a reaction between sodium thiosulfate and hydrochloric acid, and the products formed here, one of them was a solid, it was solid sulfur, and so that forms a precipitate. It's an insoluble sulfur, and that caused the cross underneath the reaction flask to disappear. So you timed how long it took for that to happen. Your investigation, well, you were changing the concentration of the sodium thiosulfate every time you did a new experiment. The technician, though, supplied us with one concentration. You had to dilute it, so you did some serial dilutions, and that enabled you to investigate the effect of changing the concentration of the sodium thiosulfate on the rate of the reaction. So you can see here we gave you some secondary data to make sure that you all had a fair chance of plotting a decent graph and analysing your results. So it was the thiosulfate that changed each time. So here for experiment 1, we didn't dilute it at all, it was just the thiosulfate, but experiment 2, we diluted it. It was a 40:10 ratio. Here 30:20, 4 here was 20:30, and 5 was 10:40. So we're getting increasingly less concentrated. And the effect of that then, we measured how long it took for the cross to disappear. So you can see it's taking a longer time the less concentrated the thiosulfate is. So as the concentration of thiosulfate decreased, the time it took for the sulfur to be produced and therefore to make the cross disappear increased. So the rate got slower. Okay, so you were given steps to follow to analyse your results and to come up with a conclusion. The first job you had was to calculate the number of moles of thiosulfate for each experiment. So here we're using our relationship between concentration, moles and volume. So we want to work out the number of moles, so it's concentration times by volume. So for experiment 1, okay, the concentration of the thiosulfate, going back to the original instructions, was 0.4. So that never changed, but the volume did. So the volume here was 50. So the moles of thiosulfate then, 0.4 times by 50 divided by 1000 gives you 0.02 mole. So you had to follow that method for each of the experiments to come up with your results. So that's what you should have got. Okay, 0.02, 0.016, 0.012, 0.008 and 0.004, and you got 1 mark for that. Okay, your next job then was to calculate the concentration of the thiosulfate in the reaction flask. So if you cast your mind back to the practical, you did it with a conical flask, you had the cross underneath, and into that flask went the thiosulfate. So you put that in, you also put the water in, okay, so plus your water, and those two combined made 50 centimetres cubed. But you also had to put in some HCl, that was your catalyst, and that was 5 centimetres cubed. So the total volume in that flask was in fact 55 centimetres cubed. So the concentration of the sodium thiosulfate in each case then is going to be the number of moles that you've previously worked out divided by 55 centimetres cubed. So for example, in experiment 1, if we take those moles, 0.02, divide it by 55 over 1000, that should get you a concentration of 0.364 mole per decimetre cubed to 3 significant figures. Okay, so that's what you should have got here. Okay, so this is what you got your second mark for. All right, so your next job then was to calculate the rate of reaction by using 1/T in seconds. So we've been given the time here, so you simply had to go 1 divided by 12 to give you your value there, 0.08333 and so on. So remembering to do that to 3 significant figures in each case. So just bringing that back for you. That is the equivalent of the initial rate of reaction now, and the units of course will be second to the -1. Okay, so just check your numbers against those. Okay, your next job then was to plot a graph. So plot a graph of rate versus concentration. Now your rate versus concentration graph, the one that we should have found that it was, is like that. If it goes through the origin and it's a straight line through the origin, then it's first order. So when you plotted your values, that is indeed what you should have found. So provided you calculated them correctly and you'd done an appropriate scale, a linear scale, this time we did need to be at the origin. So every 10 small squares here is the equivalent to 0.05. So you do need to be careful, making sure you know what each small square is equal to, and plotting it accurately with a sharp pencil, making sure you're within plus or minus 1 small square. So the data values in the table, when they're plotted, should have given you a nice straight line. Putting your ruler on, making sure it goes through that origin. You got 3 marks for that graph. A graph should take up at least half of the graph paper provided in the exam, and you need to make sure to label your axes with units, plot your points correctly, and do the line of best fit, and in this case through the origin. Okay, then it asked you to determine the gradient of the best fit line through your data points. So the gradient then is the difference in y divided by the difference in x. So if you can see here, that's those two values up there. So there's always usually a tolerance there. Roughly speaking, you're looking at around plus or minus 10%. As a rough rule, but with this one you shouldn't have had much deviation because we were all supplied with the same point and it was a straight line. Okay, so working out the gradient then, your next job was to comment on the effect of reducing the concentration, what it had on the rate of reaction. Well, the rate of reaction decreased, and that's due to the fact that there were fewer particles per unit volume, and therefore less frequent collisions. Okay, question 7 then, it said using your graph, determine the order of the reaction with respect to the sodium thiosulfate concentration. Explain why you've chosen this value. So the correct answer is that it is first order, and the reason being is that it's a straight line through the origin. Okay, they gave you the rate equation there. So rate was equal to K multiplied by the concentration of thiosulfate. We now know that X is to the power of 1, and then the HCl as well. So that's our rate equation. You were asked to calculate the value for K. So we need to rearrange that. So we have to get rid of the concentrations on the right by dividing, so they can cancel out. Whatever you do to one side, you do to the other. So that's why the rearranged equation looks like that there. Okay. Then you need to sub in the values, and this is where quite a few people lost marks. So with any of these calculations, you go back to the data and you have to choose an experiment and substitute the values in. So choosing experiment 1, you've got a rate there of 0.0833, and then you divide that by the concentration of the thiosulfate multiplied by the concentration of the HCl. Now let's just remind, the HCl here went in, it was 5 centimetres cubed. If we go back to the original instructions in the practical, the concentration there was 2 mole per decametre cubed. We put 5 centimetres cubed in of that. So again, N is equal to C times V, where the concentration is 2. The volume was 5 over 1,000, giving you 2 times 5 divided by 1,000, giving you 0.01 moles. So we actually put 0.01 moles of HCl into that conical flask. What's the concentration then? The new concentration of HCl, well, it's those moles divided by the new total volume. So again, that will be 55 centimetres cubed, because that's where those moles are now. They're in that conical flask. So divided by 55 divided by 1,000 to get it into centimetres cubed, decametres cubed, sorry, to give you a new concentration of 0.182. So that's 8. We round that 2 up, round that 1 up to 2. Okay, mole per decametre cubed. So that's where the concentration of HCl came from. Okay, 0.182. So subbing in those values into the calc gives you a value 1.26 mole. Let's have a look at the units there then. So let's see. So we've got the rate divided by 2 lots of concentration there. Okay, so the rate was per second, and then you've got mole per decametre cubed and mole per decametre cubed on the bottom. Okay, so we need to bring those up to the top, so it'll be mole to the 2, dm to the -6, second to the -1 for your units for K. Okay, so I think that's it, is it? Let's just check. Yeah, calculate a value for the rate constant K, so 1.26, and then it's best to put the units on there as well. Okay, so all in all, hopefully the thing that you've learnt from this is the fact that you've always got to think about the moles of substance, how many moles there are, and what volume that they're in, before you can work out that concentration each time. Okay, hope that helped. Thanks.